Tonight we're finishing up 6.3, and we're going to do the second half of the chapter on momentum. Your learning goals are the second two: to explain what happens when objects collide in terms of Newton's third law, and to be able to apply the law of conservation of momentum when describing the motion of colliding objects. So this is going to all be about objects when they interact with one another, when they slam into one another and do a transfer of some momentum, as we will see. Let's start off by looking at this image again, the picture of Isaac Newton on a skateboard, pushing up against an elephant, also on a skateboard, a situation that always will happen somewhere in real life. No, I'm kidding, but it's a good, funny picture to look at. Anyway, thinking about Newton's third law, every action has an equal and opposite reaction. We know that if the elephant, it says in this one, places an action force on Newton, he's going to react with reaction force in the exact same strength, but in a different direction. And we know that we can see this based upon their accelerations. Newton accelerates more because he has less mass. So we know because of his third law that any time two objects are interacting, or if they hit each other, they're going to exert the same exact amount of force on one another, except one puts force in one direction and the other puts force in the exact opposite direction. And the effect of the force is not always the same. This is what we saw in 6B, Newton's third law lab, when we saw the cars that had different marbles reacting in different ways. What you'll notice is that things that have smaller mass accelerate greater, have a greater acceleration rather. Larger mass and smaller acceleration. Take a look at this other example. When you have a large truck slam into a small car, again, we know they both experience the same force. The truck applies a certain force to the car in one direction. The car applies the exact same amount of force in a different direction. The difference, though, is the velocity in which they leave. Because the small car has a smaller mass than the truck, it's going to have a greater change in velocity, a much larger change in velocity than that large truck hitting it. So when we're looking at collisions, we're looking at a relationship between mass and velocity. And this is going to be known as momentum. Momentum is very simply the mass of an object times its velocity. The units that we use for momentum are kilogram meters per second. So it's similar if you look at that equation to Newton's second law, where force is mass times acceleration. Force, the action, or whatever the force is always going to be how much mass, or the inertia of the object, times its acceleration away. Momentum is similar. Momentum is how we classify not the acceleration, but the resulting velocities, either the velocity before a collision happens or the velocity after a collision happens. Momentum is all about its speed in relation to mass. So when objects collide and when objects interact, we like to say that momentum is conserved. Now what that means is we're looking at the law of conservation of momentum, which very simply put means that the total momentum of a system before a collision or an interaction will equal the total momentum of a system after the collision or interaction. So when you're dealing with two objects, you're talking about adding their momentums together. So look at the example to the right. You have a boy on a skateboard and a ball, and he's going to throw that ball. So prior to throwing the ball isn't moving, so it has a momentum of 0 because it has a velocity of 0. The boy isn't moving, so he also has a momentum of 0. So the total momentum before is 0. After he throws the ball away, we can say that we measure the ball moving away at negative 20 meters per second. It's negative, remember, because it's moving to the left. He moves away because of the reaction, Newton's third law, to the right at positive 0.5 meters per second. If we figure out what their momentum is, the ball, for instance, 1 kilogram times negative 20 it has a momentum of negative 20 kilogram meters per second. The boy, 40 kilograms times 0.5, has a momentum of positive 20 kilogram meters per second. Adding those together, negative 20 plus 20, gives us a total momentum after of 0, conservation of momentum. So the law of conservation of momentum says total momentum before, object 1 plus object 2, equals total momentum after of object 1 plus object 2. So look at this example. Here we have an astronaut that was in space, and he's going to release a wrench, and it's going to fly away left at negative 10 meters per second. Using the law of conservation of momentum and assuming that before he released the wrench, the total system had 0 kilogram meters per second of momentum, what is the speed of the astronaut after he releases the wrench? Pause and try it right now. The solution is we're looking for the velocity of the astronaut. We know the velocity 1 of the wrench is, that should say, negative 10 meters per second because it's left, with a mass of 2 kg. We know the mass of the astronaut, which we'll label as object 2, so mass 2, is 100 kilograms. We know that because the total momentum of the system before was 0 kilogram meters per second. Therefore, the momentum of the wrench should equal the momentum of the astronaut. It just should be different signs because the wrench moves left and the astronaut moves right, and they should cancel out and become 0. Therefore, the momentum of the wrench is negative 10 times 2, the mass of 2, negative 10, so it has a momentum of negative 20 kilogram meters per second. What does the speed of the astronaut have to be in order for its momentum to be positive 20 kilogram meters per second? Tomorrow we're going to start a new investigation, 6C. This is not going to go on your lab report. It's just something we're going to do on the side. But we're going to look at momentum, and we're going to look at collisions, and see how Newton's laws relate to momentum, and objects colliding, and objects bouncing away, and understand completely why these things happen. So have a good night, everybody, and I will see you all in class.